NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we build an intuition for absolute value and radicals. Our goal is to understand why the square root of a squared variable equals the absolute value of that variable, and how to use this safely. Absolute value measures distance from 0 on the number line. That distance is never negative. We can define it piecewise as absolute value of a equals a when it is greater than or equal to 0 and equals negative a when it is less than 0. Let's visualize distance. Here's a number line. I will place a point at A. The distance from 0 to A is the absolute value of A. When it is positive, that distance equals A. When it is negative, the distance still points to the right, but its length is the opposite of A. Now, the key identity, the square root of a squared is the absolute value of A, not just A. The square root symbol always returns a non-negative result. Example 1, let it equal 3. The point sits at positive 3. The distance from 0 is 3. And we find that the square root of a squared equals 3, which matches the absolute value of A. Example 2, let it equal negative 2. The point moves left to minus 2. The distance to 0 is 2. Notice the square root of a squared is 2, which equals the absolute value of A, not negative 2. A common mistake is to drop the absolute value and write square root of a squared equals A. That is only correct when it is greater than or equal to 0. Compare this with the square root function itself. For x greater than or equal to 0, the square root of x squared equals x. And the square root of x squared equals the absolute value of x, which reduces to x when x is non-negative. Useful consequences follow immediately. First, the product rule. The absolute value of a times b equals the product of the absolute values. Second, the quotient rule. Provided b is not 0, the absolute value of a over b equals the absolute value of a divided by the absolute value of b. Third, powers. For any natural number n, the absolute value of a to the n equals the absolute value of a raised to the n. Quick practice. What is the square root of x minus 5 squared? And what is the square root of 2t squared? Pause, think, and then check. Answers. Absolute value of x minus 5, and 2 times the absolute value of t. The absolute value keeps the result non-negative. In this example, we simplify a nested radical involving trigonometry, and then express the result piecewise over key intervals of x. We are given the expression a equals the square root of 2 plus the square root of 2 plus 2 times cosine of 4x. Our goal is to simplify a, and then determine a clean expression on each interval of x between negative pi over 4 and 7 pi over 4. Start inside the inner square root. Use the identity 1 plus cosine of 4x equals 2 cosine squared of 2x. Then 2 times the quantity 1 plus cosine 4x becomes 4 cosine squared of 2x. The inner square root simplifies to 2 times the absolute value of cosine 2x. Therefore, a equals the square root of 2 plus 2 times the absolute value of cosine 2x, which we can factor as the square root of 2 times the quantity 1 plus absolute value of cosine 2x. This compact form makes the upcoming case work straightforward. Next, we analyze when cosine 2x is non-negative or negative. To guide our reasoning, we draw a number line from negative pi over 4 to 7 pi over 4, marked in steps of pi over 4. Case 1. 4x between negative pi over 4 and pi over 4, cosine 2x is non-negative. So absolute value of cosine 2x equals cosine 2x. That gives a equals the square root of 2 times 1 plus cosine 2x, which simplifies to 2 times the absolute value of cosine x. On this interval, cosine x is positive, so a equals 2 cosine x. Case 2. 4x between pi over 4 and 3 pi over 4, cosine 2x is non-positive, so absolute value of cosine 2x equals negative cosine 2x. Then a equals the square root of 2 times 1 minus cosine 2x, which simplifies to 2 times the absolute value of sine x. In this interval, sine x is positive, so a equals 2 sine x. Case 3. 4x between 3 pi over 4 and 5 pi over 4, cosine 2x is again non-negative. So a equals 2 times the absolute value of cosine x. But cosine x is negative on this entire interval, hence a equals negative 2 cosine x. Case 4. 4x between 5 pi over 4 and 7 pi over 4. Cosine 2x is non-positive. Thus, a equals 2 times the absolute value of sine x. On this interval, sine x is negative, so a equals negative 2 sine x. Putting everything together, the nested radical simplifies as follows. Here is the problem. We want to simplify the quantity a defined as the square root of 1 plus cosine of 2x plus the square root of 1 minus cosine of 2x plus square root of 2 times the quantity sine x plus cosine x. First step, use the double angle identities. 1 plus cosine of 2x equals 2 cosine squared x, and 1 minus cosine of 2x equals 2 sine squared x. Taking square roots gives square root of 2 times absolute cosine x, and square root of 2 times absolute sine x, because a square root returns a non-negative value. Because of the absolute values, we must know the signs of sine and cosine. A unit circle makes this visual. In quadrant 1, sine and cosine are both positive. In quadrant 2, sine is positive and cosine is negative. In quadrant 3, both are negative, and in quadrant 4, cosine is positive and sine is negative. Let us simplify a in each quadrant. First quadrant, from 0 to pi over 2. Cosine and sine are positive, so absolute cosine equals cosine, and absolute sine equals sine. A becomes 2 times square root of 2 multiplied by the quantity, sine x plus cosine x. Second quadrant, from pi over 2 to pi. Cosine is negative and sine is positive, so absolute cosine equals negative cosine, absolute sine equals sine. The terms combine to give a equals 2 times square root of 2 times sine x. Third quadrant, from pi to 3 pi over 2. Both sine and cosine are negative. Absolute cosine equals negative cosine, absolute sine equals negative sine. The positive and negative pieces cancel perfectly, so a equals 0. Fourth quadrant, from 3 pi over 2 to 2 pi. Cosine is positive and sine is negative, so absolute cosine is cosine, absolute sine is negative sine. The result becomes a equals 2 times square root of 2 times cosine x. These 4 cases repeat every 2 pi because sine and cosine are periodic. We can present the answer over a full period, or using integer k to shift the intervals by 2k pi. Here is a clean summary. Using a 2k pi shift for any integer k, the same 4 formulas hold on the intervals 2k pi to 2k pi plus pi over 2, and so on. That is the finished simplified piecewise result. Example 1. Simplify the product absolute value of negative 7x to the 5th times absolute value of 2x times the square root of the quantity negative 2x squared. We first use the fact that the square root of a square is the absolute value. Now split the absolute value of a product into the product of absolute values. Multiply the constants 7, 2, and 2 to get 28, and combine the x powers. Finally, because x to the 8th is always non-negative, the absolute value can be dropped. Example 2. Evaluate absolute value of 1 minus x to the 4th over absolute value of x squared plus 1 minus absolute value of x squared minus 1. Put the expressions over a common denominator. Recognize that x squared plus 1 times x squared minus 1 equals x to the 4th minus 1. The absolute value of x to the 4th minus 1 equals the absolute value of 1 minus x to the 4th. The numerator is 0, so the value is 0 for all real x. Example 3. Simplify the product absolute value of negative 2 over absolute value of x to the 5th times absolute value of negative x to the 4th over absolute value of 2 times absolute value of x times 1 over the square root of x squared. Replace the square root of x squared with absolute value of x. Evaluate the absolute values of constants and cancel the 2's. Combine factors and cancel absolute value of x, leaving absolute value of x to the 4th over absolute value of x to the 5th. That equals 1 over absolute value of x. The expression is undefined at x equals 0, which matches the final form. Summary. In this lesson, we will solve the trigonometric equation. The square root of 1 plus sine of 2 alpha equals sine alpha plus cosine alpha for alpha between 0 and 2 pi. We'll proceed step by step and visualize the solution on the unit circle. Here is the problem statement and the domain for alpha. First, the equation. And here is the domain 0, less than or equal to alpha, less than or equal to 2 pi. We simplify the left side using two identities. First, sine of 2 alpha equals 2 sine alpha cosine alpha. Next, use sine squared plus cosine squared equals 1 to rewrite the inside as a perfect square. Taking the square root gives an absolute value, the absolute value of sine alpha plus cosine alpha. So the equation becomes absolute value of sine alpha plus cosine alpha equals sine alpha plus cosine alpha. That is true exactly when sine alpha plus cosine alpha is greater than or equal to 0. This inequality describes the set of angles we are looking for. Let's see this on the unit circle. We draw the unit circle and axes. The boundary, where sine alpha plus cosine alpha equals 0 corresponds to the line y equals negative x, which passes through the origin at 45 degrees below the x-axis. The inequality sine alpha plus cosine alpha greater or equal to 0 selects the half plane on the same side as the vector 1, 1. So the arcs from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi are included. We can also find the boundary angles algebraically. Setting sine alpha plus cosine alpha equal to 0 gives tangent alpha equals negative 1. So alpha equals k pi minus pi over 4. Inside 0 to 2 pi, the solutions are 3 pi over 4 and 7 pi over 4, matching our diagram. Therefore, the solution set to the original equation is where sine alpha plus cosine alpha is non-negative, from 0 through 3 pi over 4, together with from 7 pi over 4 through 2 pi. Here is the final answer as intervals. Example, we will simplify the expression. The square root of x squared plus the square root of y squared by using absolute value rules and clean casework. Key idea, the square root of x squared equals the absolute value of x, and the square root of y squared equals the absolute value of y. So our expression becomes the absolute value of x plus the absolute value of y. To organize our thinking, here is the xy plane. Each quadrant corresponds to a sign pattern for x and y. We will evaluate the absolute value expression in each region. Case 1x positive, y positive, then absolute x equals x, and absolute y equals y. The sum becomes x plus y. Case 2x positive, y negative, absolute x equals x, absolute y equals negative y. The expression becomes x minus y. Case 3x negative, y positive, absolute x equals negative x, absolute y equals y. The expression becomes y minus x. Case 4x negative, y negative, absolute x equals negative x, absolute y equals negative y. The expression becomes the negative of the sum x plus y. Collecting the four cases, we can write a clean piecewise answer. In this short lesson, we will decide when two statements are true. The guiding rule is the square root of a squared equals the absolute value of a. That is, root of squared equals absolute value of a. Part A. We analyze when the square root of open parenthesis negative x close parenthesis squared equals negative x. Start by applying the rule with the equal negative x. That gives absolute value of negative x. But the absolute value of negative x equals absolute value of x. Now, absolute value of x equals negative x precisely when x is less than or equal to 0. So the equality holds for all x less than or equal to 0, and it does not hold for positive x. Part B. Consider the square root of open parenthesis negative x to the fourth power close parenthesis squared equals x to the fourth. Apply the same rule with an equal negative x to the fourth. We get absolute value of negative x to the fourth, which equals absolute value of x to the fourth. But x to the fourth is always non-negative for every real x. Therefore, its absolute value is just x to the fourth. This equality is true for all real numbers. In this lesson, we will simplify two expressions and make the domain explicit. Here are the two targets. 1x times square root of x squared times square root of x to the fourth equals x to the fourth. 2. The square root of x to the sixth equals x cubed. We will prove these and state when they are true. Key rule number 1. The square root of a squared equals the absolute value of a. This is because the principal square root is always non-negative. Let us simplify the first expression step by step. Square root of x squared becomes absolute value of x. Square root of x to the fourth is the square root of parenthesis x squared close parenthesis squared, which equals absolute value of x squared. But x squared is already non-negative, so its absolute value equals x squared. Therefore, the product becomes x times absolute x times x squared. Now, absolute x equals x when x is greater than or equal to 0, and equals negative x when x is less than 0. We test both cases visually on a number line to see when the stated equality holds. Case 1. If x is greater than or equal to 0, then absolute x equals x, and the product simplifies to x to the fourth. Case 2. If x is negative, absolute x equals negative x, so the product becomes negative x to the fourth. Therefore, the displayed equality holds only for x greater than or equal to 0. Now, the second expression. We rewrite square root of x to the sixth as square root of parenthesis x cubed close parenthesis squared, which equals absolute value of x cubed. For x greater than or equal to 0, absolute value of x cubed equals x cubed. For x negative, it would be negative x cubed. So the stated equality again requires x greater than or equal to 0. In this lesson, we will decide when two radical equalities are true. First, the nested radical square root of x to the fourth equals x. Then, the square root of quantity x squared plus 1 squared equals x squared plus 1. We will use the absolute value rule for even roots to find the correct conditions. Key idea: for any even index, the root of an even power gives absolute value. The nth root of a to the n equals the absolute value of a when n is even. Example, a. Start by collapsing the nested radical. The square root of x to the fourth equals the fourth root of x to the fourth. By the rule, that equals absolute value of x. Therefore, it equals x only when x is greater than or equal to 0. Example B. Apply the same absolute value rule. The square root of quantity x squared plus 1 squared equals the absolute value of x squared plus 1. But x squared plus 1 is always positive for every real x. So the absolute value can be removed, and the equality is true for all real numbers. Final summary. The first equality holds exactly for x greater than or equal to 0. The second equality holds for all real x. In this lesson, we verify two radical equalities and determine for which real numbers x they hold. We'll move slowly and show each algebra step clearly. Here are the two statements we will justify. First, x times the square root of negative x squared minus the square root of x to the fourth equals 0. Second, 2 times square root of x plus x minus square root of 4x equals x. After simplifying, we will extract the domain condition on x. We begin with the first expression and follow the exact sequence of simplifications shown. Use the fact that the square root of a square becomes an absolute value. Then, assuming x is greater than or equal to 0, the absolute value of x equals x, which collapses the expression to 0. A quick domain note for the first line. If x is negative, the term x times absolute value of x becomes negative 2x squared, which is not 0. Therefore, the equality holds when x is greater than or equal to 0. Now, for the second line, replace the square root of 4x with 2 times square root of x. You can then cancel the like radical terms, and the left-hand side equals x automatically. The same non-negative requirement for x applies because the square root of x must be real. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.